This final video is going over differentiating functions defined in terms of integrals, basically parameterized integrals. And this is a really important topic. It's really useful. It's something I wish I had been taught when I was younger. It could have saved me a lot of time and some problems I've been asked to solve over my life. And I'm going to have kind of a preamble to problem 3. Problem 3 is the last problem in this homework assignment. So before we get to our last problem, what I want you to show you how to do is to integrate a parameterized function using that quad function, which was also shown in the lecture notebook. And that's from the integrate sub package of scipy or submodule of scipy. It has that quad function. And I'm going to show you then how to differentiate the result with respect to the parameters. This will greatly simplify the last problem of this assignment a lot. And it's just, again, it's a very important thing to understand in general. So the content is borrowed and edited from the official documentation, I believe, that you can find here. And of course, I'll have to fix that link because it's busted. They keep changing these links. So okay, I'll fix that link. So it should work in by the time you get this notebook. I'm going to go ahead and import quad from scipy.integrate. And below, what I'm doing in this code here in lines 2 and 3 is I'm going to evaluate this function. This is f of x, and I have a semicolon L. So f is a function of x and L. And I'm using a script L here because I think if you use the regular just L key, it kind of looks like 1 a lot of times. Like it's not, especially in code, when you write it, it looks like 1. Even there, it kind of looks like a 1. So I just try to use this kind of script L, which you can do with \ELL whenever you're in a math setting. So around either a single $sign or double $sign for your tech. And so then I use L inside the code as well, just because I just can't confuse it with 1. So this is it's a function of these two, but x is really the domain I care about. The thing is, the idea of the L is changing like a feature of the function, how the function behaves. It's some sort of parameter that's kind of describing a class of these functions, but these functions are a function of x. And so you could imagine, like as another example, if I go to this total cost, I could think of 0.001 and 0.002 as parameters. And basically, I could think of this C, if I really wanted to, I could write C as, let's say, R, because the R is really defining the cost. But I could put a semicolon there, and maybe I could, write like, let's say, like G and A. And then what I would do is put G here and A here, where G is the cost of glass, and A is the cost of aluminum. So it's this, if I put 0.001 for G and 0.002 for A, it's the same function we had. But writing it like this kind of makes it clear, well, as those cost of materials change, right? And we've seen this recently due to the pandemic and other things that's going on in the world, that when supply chains are disrupted, the cost of even raw goods can really fluctuate quite a bit. And so it's useful to perhaps even code this up in such a way, and then even have your function have these other parameters like G and A that you input in, and then that might even allow you to define how you should try to look for which suppliers to get the different types of raw materials in order to minimize your cost based on what the cost of how these costs can vary, because maybe one supplier can give you the glass and the aluminum at certain cost, and some other supplier gives you glass and aluminum at 2 different costs, and then that's going to change everything in terms of what the radius is, and if you're happy with the shape and the aesthetic. But anyways, I'm just going to change that back. I just want to give you an idea, like that's the idea of the parameterization. This cost function, once you fix those things, it's really just a function of R, but you might want to allow some parameterization of the cost to allow for the variability that might occur in the cost of the raw goods of the aluminum and the glass. So that's kind of what's going on here. I have this L function, or this L parameter, and it just changes some particular feature, some shape aspect of this function. But what we were interested in is integrating these functions over the x values, -1 to 1. And this is just for illustrative purposes. This actually has no physical meaning for this particular example. Which, when I integrate then this function, when I integrate out the x values, and here I'm writing dx just to make it clear I'm integrating with respect to the x parameter, not the L parameter. I know I hadn't been using this notation previously. Because there's some potential ambiguity here, I'm using it there to say I am integrating the function with respect to x. So L is just left as some value that could vary, which means that this integral is a function of that L parameter. Different L parameters will give you different integrals, and I'm using capital I for integral, not a creative choice of variable name. So here I've just coded up that function. Even though I used a semicolon here, which is usually just indicated, is used to delineate like the kind of the domain of the function versus like the typical inputs of the function versus the parameters of the function in a mathematical sense. As far as code goes, it's just parentheses. They're all parameters for the function. And here is now how I integrate that function as a function of L. So I create a lambda function for I, and what I'm doing is I'm saying, okay, quad, that's basically integrate f from -1 to 1. And it's going to do it based on the first argument, which is that x value. It's important that that x was first. And then everything else that follows in the function is just parameters. In this case, I passed this args parameter as a tuple. Then notice there's a parentheses around L, and that's it. Then again, the first output that's returned from quad is the integral approximation. This is how I create I of L, this function here. It's that simple. It's this, basically this one line of code once the function f is defined. And so now when I plot this function, which is done here, you can see it has this curvature here, and they go, oh, like there's this maximum value that's right there. All right. Let's take di dl, right? Like let's take the derivative, an estimate of it. I'll use my differences module. I'm going to differentiate using the centered difference approximation I as a function of L, again, lambda L here, with h as 0.001, just something that gives me reasonable approximations. And then I just do my typical plotting with my figure, with my two axes, so that I can have on the second y-axis this difference approximation, where again, all I'm plotting here, and I'm just looping through these dl values, which is what's going on here. Just that part of the code is constructing the array of inputs associated with each of these L values that I have here. Where are those L values? The L's. Oh yeah, those L's were given up here. Those L's. So those are the, I use linspace to create all these L values. So anyways, let's just plot that, and you'll see that where that derivative seems to pass through 0 appears to be where we maximize the function. So this is just like what we've seen before. We see that we can optimize I of L as a function of L, just like we've optimized any other function by simply searching for where its derivative is approximately equal to 0. A suggested sanity check for you before attempting problem 3, apply the various root finding algorithms, for instance, brute force, bisection, etc., that you've seen above with the pasta sauce problems 1 and 2, and see if you can estimate the L value that makes di dl equal to 0, and then plot the results to see if this is where I of L achieves its maximum. And the way I mean plot the results is add that vertical line through this plot so that you can see if that vertical line happens to cross where this maximum is. I mean, visually you can kind of see that that's what the case is, but again, it's just going to show that you know how to do this correctly. So that's the preamble. Now we'll move on to the final problem 3 that really builds on this. So for this problem, we really want to optimize our profit now. So here's some motivation. Recall, you're the world's best pasta sauce maker, and you have optimized the dimensions for your 1 liter size jars of sauce to minimize your cost per jar. This is what problems 1 and 2 were about, mainly problem 2. You still need to create these jars though. Hire and train workers that package these jars, and invest in the equipment, warehouse space, and delivery fleet for your business. Oh, and you need to hire salespersons, pay for marketing, etc. It is not only a lot of work building and running a business, it is also expensive. All of these things cost money. And so unless you inherited millions of dollars, you probably need to get a loan to help finance your dream of dominating the competitive world of pasta sauce making. What size loan should you get? It may just seem like you should get the largest loan you possibly can. After all, a larger loan will allow you to rent a larger warehouse, purchase more equipment and materials to manufacture the jars and sauce, and hire and train more workers. While that sounds great, building a business takes time. The longer it takes to set up your business means you are spending a lot of money before you are making significant money. So if you want to build a larger warehouse, you're going to wait longer until you're actually shipping the sauce. And then guess what's going to happen? The loan's going to come due, at least the first payment of it, and you might not have any money yet to pay it because you were just building out the infrastructure for your business without actually making money yet. Oh my, right? This is a problem. So larger loans also will often come with bigger interest rates and significantly larger quarterly payments on the loan. So in the end, you may run out of money if you try to make everything too big initially. What happens then? Your lenders take over your business. They liquidate it, sell it to someone else who becomes the owner of your intellectual property, in this case, your special pasta sauce recipe. And they maybe even come after your personal assets if you put them up as collateral. So in the end, getting the right loan amount and making a strategic plan based on a certain amount of the loan is perhaps not as straightforward a problem as it may seem. That leads us to defining the problem. Suppose you are qualified for loan amounts between $500,000 to $1 million in U.S. currency. Let L, that's script L, denote the loan amount in units of $1 million US dollars, which means in those units, L is between 0.5 to 1. Let capital M of T, semicolon L, in units of $1 million US dollars, denote a model for your projected net cash flow at time T, in units of days, if you follow a business development plan that's based on a loan of size L. So for different loan sizes, you're going to have different plans about how you deploy that money. And so some of them will allow you to potentially make some money right away, but maybe not as much money later on. But you have to figure out that the model is only valid for 90 days, the first fiscal quarter of your business, and that might be when the first loan payment is due. If M, capital M, is greater than 0, the interpretation is you are making money at time T. If M of T is less than 0 at time T, you are losing money at time T. The total amount of money you're going to have made or lost over the first 90 days is the integral over 0 to 90, M of T, semicolon L. And again, that's dt. We're integrating with respect to T. This is a function of the loan size, the total amount of money you have. Your problem is to optimize T of L over 0.5 to 1. You want to maximize the total amount of money you have after 90 days because you'd like to not lose your whole business. So your job is to do the following. Use the function money that's defined below. It's this 3 lines of code. You need to determine what the optimal loan size should be. So no, I'm giving this to you. You do not need to code what the money function is, really even understand where I got it from. I'm just using it for creative, illustrative purposes. But it's a function of T and L. It returns M. What you need to do is compute T of L. Basically, I'm using M, where up here I used F. I'm using capital T of L, where I used I of L. You're basically going to follow this as a template, but not blindly. You need to think about how to code up your integral for T using the money function, which shouldn't be F, and it's not over -1 to 1. It's from 0 to 90. Like, pay attention to the details. If you just start copying and pasting without any paying attention to details, you're going to miss all the points. It's not hard. You can copy and paste some things, but you need to be strategic and really think about what needs to change. And what you need to do is make sure to put comments in your code, provide useful annotated graphs and illustrations of results, and interpret results in markdown cells. In the end, you will have done this right if you find that the loan amount, if I recall correctly, it's somewhere in the 800,000 region. I think that's correct. If I'm wrong, I'll post something on Canvas about that, but I think it's in the 800,000s, I think, is around what the right loan amount is. So the L value is like 0.8 something, I believe. So I'm kind of pointing you towards that. That's a sanity check. It's not on 0.5. It's not 1. It's somewhere in the middle. I think it's around 0.8 something. It's just been a while since I've done the computations myself. That's what you've got to do. You just got to solve that, explain what's going on, interpret the results. You got it. Good luck.